Okay, so today, people, I will present for Joel, and you probably will just remember Nathan because he probably forgot already. I the process that of making a language, not the internal details, but the main points or and the lessons learned that we got from this process, right? So I will present the language. It's called Silverware, and it's made by me, Nathan, and Mageta, in which we developed in a couple of months, I guess. So let's start. So the first thing that we need to talk about is which language, not languages, which features slash inspirations you're gonna take to make the language. Right. So the first thing that we wanted as our inspiration, in which the keyword is inspiration, is Common Lisp, partially because we want to have an easier time parsing the S expressions, and we also appreciate not having to take care of precedence whatsoever. That's 100% less one headache to have because you don't have to take care of that. The next thing is that we want the language to be statically typed because all three of us are suckers of statically typed languages. And we also want to have functional programming as a core concept of the language. So we would like to have records, pattern matching, parametric polymorphism, and just for the record, because this will encloses multiple languages, right? Nathan prefers OCaml, Mageta prefers F#, and I prefer Haskell. So we have a lot of ideas that we can fuse together in order to make the language that we wanted the language to have, right? The next part is that we need to talk about software development because if you're gonna make a language or any piece of software actually, you need to take care of what strategy you're gonna use. And usually, a very common approach that we use for making software is an ad hoc approach, which is basically taking what works, and usually you have some sort of legacy, right? So you do what people already have done and it worked for them. You take that into consideration, but you don't have any sort of formal slash theoretical background in order to sustain your ideas, which is actually the other way around. So there are more approaches to it, and there are also mixing both of them. But I want to emphasize those two because these are the things that we use to make silverware. We took both ad hoc approaches, and we also got inspired by some sort of theory. So talking about theory, I want to talk about the theory that we used for it. So we used SystemF as the baseline for the language, which is basically second order lambda calculus or a simply typed lambda calculus, which is one layer above what Church developed. And just for simplification, I have the identity function in SystemF. So this identity function can be read as given a type alpha and a value x of that type, you're going to return x. And after the column, we have the type of the entire function, which is for all alpha, receiving a value of that type, you're going to return a value with that same type. So you can read the inversed v as a lambda, but for types. So it's not big of a deal. I'm not going to go into much detail right now about SystemF because that's not the point of this talk. If you want to see more of SystemF, you can. I recommend this talk that Nathan gave about that, and there's a bunch more things going on there. So this is the foundation, right? SystemF is the theoretical foundation that you're going to add ad hoc layers and ad hoc features on top of it. But we are trying to use SystemF in order to avoid some bugs that the theory can assure us that we are completely safe. So that's important. So let's start about the history of silverware. So silverware would be initially, and it still is, interpreted language, which means that we are not compiling the language. So we are dividing the thing into two parts, the parser and the interpreter. But these are lame names, so we need to make them better, like that. And we're going to have the knife parser cutting things and then providing that to the spoon interpreter. So one part that we wanted to leverage doing this part of the process is try to explore different languages to do these two parts, but we didn't want to mess around with having to interrupt them. So we want to be able to have different languages, but it's not complicated in order to them to interact. So we need to actually choose an environment. So we had a couple of ideas in mind. So we had the .NET environment with C# and F#, and we also thought about using the Erlang environment because there's multiple languages in that environment. We chose the latter, so we chose to use Erlang-based languages. In the case of the parser, we chose to use LFA, which is basically Lisp, but inside the Erlang ecosystem. And this, because it's a very obscure language, we needed to actually create a parser community library from scratch, right? Which, at least for me, it was a ton of fun, but not everybody enjoyed that. And it took us about this amount of time from July 30th to the September 24th, about 2 hours per week working on it. We completed the entire parser of the aimed language. Next up is the interpreter, in which we did in Erlang. And one key point that I want to emphasize that will matter later is that pattern matching, we discovered that pattern matching is a must-have to make the type of language that we are interested in making. And it also takes the same amount of time, also 2 hours per week, so 4 hours total. Two for the parser and 2 hours for the interpreter. If you want to watch us struggling with that, you can. This is also publicly available. So these are basically a compilation of 3 guys suffering with a language that they don't know, and they are trying to know enough in order to make what they want. And you can see that you have only 17 videos combined, right? And okay, so this was the process of making silverware, and this is the most advanced program that we made for silverware, which is there's multiple lines in here, but it's not that much things happening. But I will explain line by line in order to be clear. So this is an example of an application, right? An application is composed out of 2 parts. We have the abstraction and we have the argument. The abstraction is also can be called a function. So the thing that is highlighted in here is actually the function part, right? And in this specific function, we have some parameters, right? And in here we have the x being an integer, the y being a boolean. Z is a function that takes 2 integers and returns an integer. And we also have a numbers parameter, which is a list of integers. And it's actually an arbitrary amount of integers with the ampersand, right? Which, as far as I know, is also very common in Lisp-based languages. So these are the parameters. This is the body of this lambda, in which we verify the value of y. If it is true, we're going to pick x and true and apply that to the z function. And otherwise, we're basically going to do a fold with a plus within all the numbers that we acquired. Yes. And now this completes the function part. We need to provide arguments to this, and in this case, we need 4, right? So the first one, which is an integer, is basically doing a condition and some Boolean operations, and also doing some arithmetic operations to produce the integer, right? So you're going to sum 1 to 4, or you're going to subtract 1 through 4. Again, it's basically doing a fold. Next up, we need to have a Boolean. So we are basically doing an AND logical operator and negating immediately afterwards. Now we need a function. So we need another lambda just for this one. In which we pick the 2 integers and sum them up. And finally, we provide 5 numbers, in which the 5th is actually generated via multiple order arithmetic and logical operations, just to exemplify what is available in the language itself. And that's about it for silverware, right? But you can look at that and just say, dude, this is completely not enough. How can you make even some simple problems? How can you solve even simple problems with this? You only have application. You can have any sort of functions and any sort of higher level abstractions, such as records or types or anything like that. And that's why actually we decided to make a second version of the language, which is called Silverware Plus. Silverware Plus is much more than Silverware. In fact, it's that much more that actually deserves to have a section just for the theoretical part, because Silverware Plus implements System F Omega, which is an upgrade on top of System F, which adds kinds to the game. So you need to also do kind checking on top of type checking. And this is the book that we use as inspiration for the kind check function that we implemented. So now we need to talk about the differences in the history of Silverware Plus. So instead of doing two things in two different languages and have to interrupt them, we're going to make a single thing that will do parsing and interpreting. So, and because we're doing a single thing, we can also just pick one language. And in this time, a language that we have a little bit of more familiarity and we know the features that we also know the features that we need as a must, right? So we need some sort of library support because we don't want to write the parser combinator library from scratch. And we also need pattern matching because we need to find that as a must in the Erlang version. So we went with Haskell, in which we used, there are multiple libraries for parsing, there are multiple features to have safe code and etc. And in terms of the features that we added on top, we will be able to add a REPL, algebraic data types, records, a prelude, and even some sort of pattern matching because it is still not yet complete. There is a bug on it, and I don't know exactly when we're going to fix it, but at least we are aware of it, which is already progress. And this software adventure can also be watched publicly in much more videos this time. And we actually didn't record the entirety of the process because sometimes we actually recorded 2 hours and spent 7 on it, just in order to debug and make it better offline, right? So that's the end of the history process, right? So Silverware, from Silverware Plus, from Erlang languages to Haskell, and what were the lessons that we learned throughout this process? So these are the languages, not the language. These are the lessons, and I want to go one by one because I think they are each one of them deserves some time. So then the first one is about the static checking when parsing, because we use parser combinators in which we depend on the types. We need to also fulfill the type system, and this, it is a little bit of a mixed bag because at the same time that you can learn a lot from parser combinators in terms of the abstractions that Haskell provides, it is still a hassle because it doesn't. We spend a much more time doing that as we wished, and we could have spent that time doing other things like the type checking or the kind checking or any other multiple other things that we have to do in order to make the language. So, and this is very this is a truthful statement. If it compiles, that does not mean it works, and this is the peak of this example. It maybe it will compile, but that doesn't mean it's parsing exactly what you want. So of course, this can be mitigated by practicing. If you are very, very used to some parsing library, you can get up to speed very fast. But in our case, we are just like, we know the base of parser combinators. We want to get through this to get to the real deal, which is interpreting and evaluating and checking things. So it is a point of discussion. Which strategy for parsing you're going to use? Next is that the theory is very scary, right? And this is very common in any sort of mathematical-based theory. We are usually very scared of Greek letters, which is okay. But the point is that we cannot ignore this because this is too powerful for us to ignore. And the only solution to this is instead of being scared and just be consumed by that fear, you just practice that. You spend some time making something in the real world that uses that theory as the base. And with that, you can just avoid ad hoc solutions, which is always great because you have more things backing you up, right? You have more things saying that you potentially you have a very high chance of being right, or you have a very high chance of not encountering certain bugs. Next is that doing this sort of process, you start stopping taking things for granted in other languages, because we meme about certain languages that they don't have, I don't know, pattern matching or a strongly typed system, and when you do them, especially the pattern matching one, you start valuing those a lot more because you see how hard it can be. We spent take or less more or less 10 hours of trying to implement the pattern matching, and it's still not done. So you start stopping like saying, oh, this is, if you don't have this, you are completely a toy language, because sometimes it's not that easy, especially if you add extra things on top. So you have the pattern matching, but you need to consider this and that and this that the language already has. So this is definitely something to be aware. And then next part is the lesson is about, do not try to be fancy from the beginning, right? Because in the beginning you have a lot of ideas throughout your brain process, the brainstorming process, and adding noise would just make that process much harder. So if you have, for instance, the organization of the files, how the project is organized, if you try to keep that organized throughout the entire process, you may have a problem um, um, thinking about the things that matter. You don't want to think if function X should be in this file or in this. You want to actually be thinking about, is this X function doing what I actually want it to do? That's what you need and want to think about. And noise is it's something that you should avoid. Later on, when you have the ideas consolidated, you can make it pretty. And following best practices like file organization and naming conventions, etc. Next is that doing little by little, you can go very far. More, even like you not expect to go that far, but when you look at the bigger picture, you did 15 minutes or 30 minutes or 2 hours in one single week, and then in a matter of 2 months, you did a lot. And that is something that I think it's very uncommon in the community. People want to start projects and finish them in like 2 weeks, even if they are very ambitious. You need to take your time, not only to learn, but also to enjoy the experience. Because if you're going to put that amount of pressure on trying to solve it as quick as possible, you probably, first, you're not going to think right, because ideas need to digest in our minds. And second, you're probably going to get pissed or tired of it, which is not a good thing at all. And finally, is that pair programming is so fun. And it is underestimatedly fun. So doing that, you learn how to explain your ideas better. You actually try to see if you understand what you think you understand better. And you also hone your communication skills. You make them better. And for me, it's completely not a difficult decision. Between this and any sort of happy hour that people have, you just need to wait for me to grab my water while you open your text editor. For me, it's no doubt. Completely easy. And then the question that remains is that, is silverware done? And that's fair, but the answer is no. So these are our list of to-dos slash features that we wish to have, that we want to have in the language. So on the left, you have the phase that we already completed, in which we have all of those. Notice that the pattern matching has an asterisk there. That's important. We phase 1.5, which is the features are less complicated to implement in theory in comparison to phase one, but we want to do this less often because we want to explore other things at the moment, because we are saturated of doing this for 5 months. So there's that. And we also have future plans, really, really long-term plans for the language, in which involves features that I don't even know what they are, but they are there because somebody mentioned them. And I'm not completely. This is like a lifetime project because the expected time is like 3 years just for these two phases, right? So in 3 years, you're gonna have a compilable with multiple type safety features, all the things that we want. And there are some things that may conflict with one another, like type classes and object system. Maybe this is actually not feasible, but we're gonna know by practice, right? We're gonna suffer first in order to say almost dying that doesn't work, because we're gonna try very hard to make it work. And that's about it. But I know that I'm missing something, right? I am missing the Silverware Plus program example, and that's the next phase of the presentation. So now I'm going to just open Emacs and show you how the thing works. So this can, I think you guys can still see my screen, right? Are you guys seeing Emacs? Okay,
Yes.
so instead of showing you the features of the language, I'm going to show you showing a problem that I solved using it. I think that's better. So the problem that you're going to solve is this one. We're not going to read through this. There's a lot of text in here. What you need to care is actually the input, which is this set of numbers. So our goal are twofold. We have two questions to answer. The first one is which group is the biggest one, and each group of these numbers is divided by an empty line, like this one. So yeah, like that, I think it's better. So this is a group, this is another group, and this is a group again, and you need to define which one is the greatest one. And after that, I want you to give me the three greatest ones instead of only the top one. And I have the answers already because that I did when I did in Haskell. So 72, 602, and you also have 20, 74, 10 as the answers. Right. So this is the solution to that problem. And I'm going to explain the solution as showing you the features of the language and explaining as I see fit. So the solution to the problem from a high level perspective will be a fold, right? So we're going to fold that input that is divided by new lines. We're going to read a file that contains the input. We're going to divide it by new lines. And now we're going to do a fold in which we're going to always carry the greatest group. So this will be the number that we are currently summing up, right? So this is like if you have a group, you sum the first, the second, and so on. And this is the current max, which is the current greatest group that we have. We're going to carry that over throughout the fold and update as we check for some conditions. So the part one of the problem is that this is the function that defines the part one of the problem, right? And each part has its own function. And we're going to go through the main points of the solution. I'm not going to go through that much detail because some functions are just tedious, like this one. But the main idea I will explain of them. So the first thing that I'm doing here is actually defining a parametric record. And because Silverware Plus doesn't have yet type inference, we need actually to specify the kind of this. So you're going to receive a type, and you're going to put that type in the current max. Because if you remember, in the first part of the problem, we need the current max is a number, but in the second part, the current max is a triplet. So we want to be able to reuse this. So for the part one, we're gonna have we're gonna define an alias, applying an integer to the parametric record, which makes basically this t an integer for this specific instance of single. Okay. And now we can go to the main function of this part. So this part one function will receive the input path as a string, and it will return a unit because it will print something. Then we're going to define some variables to use, such as we're going to read the lines of this file. We're using a function that we provide in the prelude. And then we're going to create our initial accumulator, because again, we're going to fold, right? And then we're going to create this instance using 0 as the values for the initial accumulator. And then again, this bang integer and bang string and etc. All of these is because we don't have type inference, so we need to specify the types for these polymorphic functions. So this is the type of a single element in the container that we're going to fold through, and this is the type of the accumulator. And then this is the function that we're going to use to fold. This is the initial accumulator, and this is the container. And after we fold that, we're going to actually pick this record that is going to be generated by the fold. And we're going to get the field current max out of it, which is this one. And then we're going to print that. And because we know this is an integer, we're just going to say to the print that you should expect an integer. And now the folding function, which is this guy. This guy receives one element of the container, which is a string in this case, and the type of in an accumulator. And then we return a new accumulator out of that. So the first problem is that we need to define when a group ends, right? And then, as I said, a group is defined by an empty line in the input. And that's exactly what we're checking with this if. If the string is empty, that means that everything that we had on our current is actually the sum of that group. And now we need to check if that current is actually greater than the current max that we are holding. In the opposite case, which is the case that this is not empty, we're going to go through this thing, which is that we're going to actually pick the calories, which is what that number represent, and transform those to integers, because those are in a string form. We're going to give that a name. Then we're going to sum the current field of the accumulator. We're going to sum that number with this and get a new current. We need to update the accumulator. So we have a set function for records that allows us to pick this field and update with this value for this record. And we're just going to return the record, the new record, right? The new accumulator. But in the case that we finish the group, which is the true case of this if, we only need to check if the current value that we have holding, which we are calling candidate, if that is actually greater or not than the current max that we are holding. Because if it is greater, we need to update that, and we are doing that with the set. Otherwise, we just put that to 0. Actually, we do this all cases, right? We finish a group, we need to update the current back to 0. But in the case of not being greater, we're only going to do that. We're only going to have the 0 here. But in the case that it is greater, we need to set that. So the current max is actually the candidate that we just established. And that's about it for part 1. The main difference between part 1 and part 2, like I said, is that the second one uses a triplet instead of only a number. So we're going to make an algebraic data type for that. We're going to call that triplet, and it has a constructor and 3 numbers inside, 3 integers. And we're going to make another alias using the same record that you used before, but instead of an integer, we're going to put a triplet. We define some global variables in here that you're going to use to do the evaluation of greater than or smaller, because now we need actually to update 3 values, right? So as you finish a group, you need to check out all the possible values in a triplet to actually remove the smallest and update with the one that you just have on hand. So this is the part 2 function, which basically is doing the same thing, but instead of initializing the accumulator with a record, and it is initializing it with the ADT, with the algebraic data type. And something that I forgot to mention in the problem description is that after we discover the 3 greatest triplets, we need to sum them up. And this is actually being done by a function that we are defining here in this let block. So this is actually a function that does a sum. It picks a triplet and returns an integer. It does pattern matching to extract the values that we have, and then just sum them up. And everything else is basically the same. So you pick the lines, you read the lines using the new line as a separator. You create the initial accumulator as well using the initial triplet. The current is also set to 0. Then you ask for printing an integer because you're going to use the sum, which you will transform the triplet to an integer. And then you're just going to fold. That's about it. We need to adjust the types accordingly. So instead of that alias, you're going to use this one. And that's about it. The function to update is applied throughout the fold is basically the same, but instead of doing that comparison of less than that we are doing in this case here, I actually needed to create a special function for that, because again, you have 3 numbers on your hand and you have a new one, you need actually to compare 3 times, right? Because of course you can make, I don't know, a queue and just have like a priority list or something along those lines in order to make that happen, but I didn't want to bother to make that. So I'm just checking 3 times. And that's about it. And then the solution itself is a function that takes unit and returns unit, and it just calls the 2 smaller functions for each part, providing the input path for the file which has the input. And then we just call the function down here, passing the unit value. And the question is, does it work? That's fair. And then we can just do that, which is basically calling the interpreter passing this file to execute, the file that I just explained. And it works. So we have 72, 602, and 207410, which is the answer that I did in Haskell. And I know it's correct. And one thing that I actually want to add is like we already started adding some sort of error support. So let's suppose that instead of T here in the record that I'm receiving a T, I'm gonna put whatever letter I want, so like K, right? And then let's see what happens with our example here in the terminal. So it's saying to me that in this file, this line and this column, we didn't find anything, an alias in this case, K in the environment, which is how we report the errors. So yeah, I think I'm done. I hope I didn't just vomit words. So questions and comments.
Yeah, I have one. So, why would you do different if you were to do that like all over again?
What I would, well, I don't know about Mageta and yourself, but I would try to give my answer. So what I would do differently, I will consider a little bit more the parser generators. Not because I think they are better, but because they are faster to implement. So you don't have to mess around with a lot of the corner cases that we had to mess around because we chose parser combinators. Like I said, it's gonna compile, but that doesn't mean like usually that means nothing. So doing the parser generators would be maybe faster, maybe better. I don't know. Probably it would be a little bit more unpleasant in my opinion. In my opinion, okay. But maybe that would get us going faster. What else? I will actually search a little bit more about the Haskell support for libraries because there are multiple libraries that they do essentially the same thing, and I should have picked better instead of picking the first one that appears on Google. So, for instance, we are using TextParsec. As far as I can tell, there's a disciple of this library that is better called MegaParsec. And I don't know how smooth would it be to upgrade. People told me that it would be very, very easy because the names are the same. But I would definitely check for better support for libraries. And I would also add testing, right? We at some point in time we decided to stop testing the thing. Like when I say testing, not this type of test that I just shown. It is like testing, property testing. You say stack test, and then it's going to test a bunch of properties and a bunch of use cases that you know should work regardless. After some point in time, we got to the point that it was so complicated to make a test that we stopped doing it. And I think that if we did from the beginning and just doing iterations, upgrading the test will not be that much of a hassle. I want to hear from you guys as well, Nathan Mageta. What would you guys do differently? So you can answer that as well.
I'm not sure about what to do differently. Maybe I think one of the regrets I have is the lists. Like we were not using, for example, but I think like there are some other things that we didn't do yet, right? So for example, I think our like the way we are handling the amount of things that we added in the language just to cope like some random problems that we were facing on parsing kind of, you see, like for example the bang on the integer,
Yeah.
like that's one example that I dislike.
Yeah.
But I think like most of the features that would complain right now, it's because we haven't made yet. So like inference mainly, I think
Yeah.
the types everywhere pollute a lot the language, but that's not
Oh yeah.
really a feature I would, I regret because it's not implemented. So
I also have another one that I just remembered. I regret not making it compilable in the beginning. Because if we had that compiling already,
okay.
maybe doing extensions will not, because right now we have a big monster,
Yeah.
right? We need to figure out how to compile everything top to bottom. We don't have the option of having a subset of the features. Everything depends on each
Yeah,
other.
basically we
So
should start fresh, like basically again, right, to do the compilation at this
No, we
point.
don't need to start from fresh to do the compilation, but we need to be very creative now if we want to maintain the current. We want the current what we already established, and we want to compile that. I'm completely sure this is going to be a lot harder if we just made it in the beginning compilable, and then when we add a new feature, everything stops. Make it
Yeah,
compilable again.
I kinda disagree. It's not that it's harder or it doesn't fit with our implementation. It's just that it feels like a lot of work because we are not doing like iteratively as you said, Lemos. So it's
Yeah.
not harder that we can't. It's just that it feels like a lot at once. You see?
Yeah, no, but it's gonna be harder. For instance, maybe the book that you're gonna choose to do the function, how to compile functional languages, it's gonna just say talk about simple typed lambda calculus. And then what you're gonna do? We have a lot of other things on top of that. So
Yeah, they don't matter, Lemos.
I don't
As
know.
in,
That's my concern. I don't know at all. I would know if we had done from the beginning. So yeah.
yeah, about my regrets. So I have a lot about the syntax, dude. About the syntax and the parser. Uh, so yeah, I don't think we are really leveraging the syntax
No, we're
because we
not.
are not doing some meta programming that you use the
I think we
list
are
structure.
in large re-implementing a lot of things that macros would solve. For example, like with the syntax, for example. So we opting not to implement some features. Basically, just like kept ourselves and delegated all the work to the actual interpreter.
I'm not completely sure what you mean by that, man.
Like for
Because
example,
we only have a type system, so
well, there's a syntax. For example, ifs, like our match thing. Like we made a special structure
oh
for that. That could be just a macro, you know.
yeah, okay. Now I see. I see. So the core language could be smaller,
Yeah.
and we could have like macros for. Yeah, but that doesn't need to be the case. We can do that without macros.
No,
No, we
yeah, but
can. We
I'm just
did.
saying, like
But
Yeah, we
we.
did for some things, right? Like some
yeah.
syntax sugar.
No, we did syntax sugar, but only for the internal behavior. So for
Yeah,
instance,
like
when
program
you actually
on
create a
the form.
record, not only that, but when you
What
create a
I mean
record,
is
this is a
something
function,
like
right?
wait, what? The function?
Yeah, when you create a record, the fields are actually translated to functions internally. The user cannot think in that way because you need to use the setar and the getar as the API for the
You
records.
mean a sum type?
A sum type, I don't think so. In the records, I'm completely sure. We transformed the fields of a record, anonymous or nominal records, by the way, because this language supports anonymous records. The fields are actually transformed to functions because you wanted to copy Haskell in this sense. But when we decided to make the API to interact with the records, we use that inside, but the user don't, which is
Yeah,
actually a weird decision. But
I can't remember that part, but I'm pretty sure we did some simplifications on those things. And that's a trade-off. You lose some stuff.
yeah,
Some information is lost, and you have like worse error messages.
yeah,
And well, regarding the syntax, it's more about that. We have the quote unquote S expressions because they are getting out of X expressions in a few places, but we are
yeah,
not leveraging that for meta programming and stuff. And the other
yeah.
thing is our parser itself, because I'm not sure if I would go for the parser generator. Probably would my uh, my choice. But the thing is, it's not only about that. But one approach we could have done is doesn't matter the kind of parser, you parse as a quote unquote generic S expression. So it doesn't say much about the structure, so you can't do much with it. It's something like a parse tree, and then you have a different pass from that to the actual AST, and you can
Oh,
do
I see.
that just by pattern matching. I think would be a whole lot easier. The parser would be like a few lines, dude, with parser combinators.
Oh, you
Like
mean so we have a big parser, a S expression parser, And then inside we do some sort of pattern matching. Will not be pattern matching because I think we would have to pattern to match strings, which would be
Yeah, still
terrible.
pattern matching.
Yeah,
Yeah,
but
yeah, we probably would need a bunch of utility functions to
yeah,
validate
yeah,
a
exactly, exactly.
non that in a non terrible way.
Yeah,
So
I agree, I agree.
yeah, I also have a blog post that might help us in the future, and he talks about his experience that he had doing a compiler and stuff on if you go def first or breadth first, like implementing all the features in
Mhm.
a simplified version and then going on, or implement one feature and go all the way, and then you implement others. So yeah, I would probably do something more like, okay, once we start to implement something, implement it properly instead of just a simplified version, and then you never go back to fix that. So
No, but
yeah,
that's because of our model, right? Our model is basically when you get something done, if it's a simplified version, it takes us a lot of effort to go back to it because you want to go to something else. I agree
yeah,
that we should not have done that in some cases. So the what is the worst case that we did that?
yeah, it's probably substitution.
Probably substitution. Yeah,
Yeah,
okay,
it
that's
Wait,
fair.
kinda doesn't
substitution
really
why?
work for some cases.
Yeah, he's talking
Uh,
about the ID thing, right? That you're using identity instead of
yes,
using
Oh,
the
okay.
number.
Yeah,
that's
yeah.
exactly it.
Yeah. So just to people to get context, in the substitution process of like the lambdas that we are doing and stuff, because this is all being converted to lambdas at some point in time, um, there is a problem that System Omega explains. I don't even think it's Omega. I think even System F, normal System F explains that, which is that you can have some conflicts with naming, and then the solution to that is adding an identifier to the parameters of lambdas. But these numbers, they need to be different because they need to be unique, right? And that part we didn't do. That
So
part we
yeah, it
didn't do.
works like normally, but for some edge cases, depending on what names the user chose, it just fails.
Yeah. So we still have to fix that, and I agree that we have so many other things to do that are classified as more important that we still have that dependency on hanging. Like we need to fix that. Um, but yeah, that's a good point. That's completely fair. Uh, okay, so other questions. We just answered Nathan's question. Or comments, can be comments as well. Whew. Oh man, I talk a lot. I hope I didn't talk too fast. Okay, so if you don't have comments or questions, I think we are good to end. So, Mageta, last words?
Well, last words. What are you implying?
Yeah, because if we're gonna finish the recording and stuff.
Okay, so that's it. I think I hope we make another presentation with this, like this less code to show actually on this same problem, and that's it.
Oh
So
yeah, it would be nice to have a version that solves
yeah,
the problem with
that
less code.
abstracts a little bit more some stuff there.
Yeah, yeah.
Anyway,
We need to add some more like useful data structures like priority queue and stuff, and like
yeah,
support for trees out of the box.
a
More
mailbox
more stuff.
processor.
Mutability. Oh man, there's so many things to do yet.
Yeah, tooling as well,
Nathan,
right?
last
Now that
words.
If we have an
now that you're
LSP,
talking, Lemos. Sorry,
Sorry,
Mageta.
Joao. Joao.
Now that you talked, how do you guys are handling threads?
We
oh,
don't.
we don't. There's no threads.
Oh man.
Yeah, so it's pretty naked, the language. There's not much there.
Yeah.
That's the
I
main.
see.
We kind of have something, but that's not for this specifically, but for anything, any feature that you ask. And that is, we have some interrupt with Haskell because we are just having Haskell to run our code. So you can just call any Haskell function.
Yeah.
So a bunch of stuff that Haskell has as functions, you can call it if we create a well, if we put it on our
Prelude.
standard library, so you can just call it.
Yeah, like for instance, threads that you just asked, we could add like in a library that we have control, the standard library, we could implement asking Haskell's way of doing threads. And because this is not self-hosted, and I like if we get to the point of making this self-hosted, I would be amazed and surprised. Then we would have a different conversation. But yeah,
Yeah, we need. Before I'm actually up to try to self-host this, but I think we should spend a bunch more time like trying to make the experience better.
yeah.
Like error messages, I think they right now they suck. Like they're really bad. They're still better than the ones that I'm getting at TypeScript, but they're better. They're bad. So
They are better than.
Well, to be fair, I was taking a look literally yesterday. I guess it was a newsletter or something like that from Okamo of things that happen in the week, and they just implemented a error message for something like when you have a value and you are trying to apply that on a value, right? So you don't have a function applied on a value. Like it's a different kind of value,
Yeah, applying
not
one
a
to one
function.
basically.
So yeah, they have a really bad error message for that. They fix it just now, man. So yeah,
We would save something better than that.
yeah, we could have done something better than that.
I think that the error messages are not that bad now that you can know where, right?
no,
Because
okay,
when you
that
didn't
is
know where,
better.
that was
Yes.
like.
That's better, but still not optimal, right? There's a bunch more
No, my
info.
final goal would be to read the file in which the error occurred and point at the character that
Yeah,
the error
one
starts.
thing that annoys me. We don't accumulate errors. For example, you stop in the first error you encounter, right? So I
Yeah,
think it would be better like trying to continue a little bit further and trying to map and so okay, I got an error here, here, and here. So like you don't have to keep one by one like compiling.
yeah,
See?
exactly. That's a good
Yeah, but
point.
that's quite tricky because if you have an error, the rest of the stuff that you are doing, they might be influenced by the first thing.
Yeah.
So you see, especially when parsing, that's a bit complex, dude. If you had an error like here in the beginning and you have another error later,
Mm-hmm.
maybe the later is not an error. It's just because of the
Yeah,
first
of the
thing
previous
you
one,
got
like a
wrong.
type or something like this that got skewed. Yeah.
Yeah,
So
the parsing problems I think is going to be very hard to accumulate, but the ones that happen on type checking time or evaluation time, maybe those ones we can get around because this should be an integer and it is in a string, but everything else is like properly parsed. So you have only like three S expressions, for instance. If the first and the
well,
third are wrong, you should be able to tell both.
evaluation. I don't think there is such thing because once you have one error, it's really done.
No, in the case, maybe evaluation I am underestimating, but type checking should be okay to like
Yeah, we
accumulate
should take
that
a look on that.
and
It's
then just
probably
go
more
on.
feasible. Yeah.
Yeah, the type checking sounds like smells more feasible. Maybe I'm completely wrong. Because every single feature, I think we can say this for sure. Type checking is the most difficult part of this
I
because
guess.
after you're done with your headache of the parsing, the evaluation is usually like 10 minutes, and then all the other hours are in type checking. So that's usually how it goes. Um, so yeah, that's a good point. The error message we need to make it better as well. The error reporting system. That's very fair. How much time do you have in the recording, Magetta?
49 minutes.
Okay. So yeah, I talked really fast then. I'm sorry.
Yeah, that's fine.
Yeah. So I think that's about it. And yeah, no, Joao, we don't have multi-threading.
Yeah, we can add
Even
easily.
I don't even know when we're gonna implement that.
Oh, we can add it now. Like it's not that hard, I guess.
It's well, kind of. Something also that I should mention is that we tried to add some sort of naming spacing or module system as different than just loading a file. This is literally just picking that file and gluing it in here, copy pasting it. Um, but that didn't go well as well because we wanted to make it dumb first, like not completely properly, because making it properly it seems very hard. But making it dumb is hard as well. Maybe it's actually faster to just make it properly on the first go instead of trying to make it dumb in a dumb way. I mean. So yeah. So I think that's everything. Commander, are you not gonna comment that you cringe on the syntax?
No. I mean, after you explained to me that this is not a Lisp, it's just you know, it's just the shell of a
It's
Lisp
just
Yeah.
on
the
top
hollow
of everything.
shell.
No, I'm fine. I have no comments on non-Lisp.
It's just
Okay.
because we need parentheses to attract people into the link.
Yes, yeah.
That is
That's
exactly the
the real
reason.
truth.
That strategy is not gonna work, but you'll see.
That's a very fair point. That's a very fair point. Bro, I'm very okay with the syntax, being honest, because we need to improvise some things because Lisp doesn't have any sort of type system at all. So, well, at least that I'm
Hey,
aware.
That's
that's
a
not
false
true. I
statement.
even told you
No,
about
I'm
it.
not talking about what happens when you execute the code. I know there are types there, but I'm talking about making explicit like, oh, the return type of this is that.
No. Even that is there.
I'm completely not aware then. I'm sorry.
We did that, man.
Man,
No, I
I
didn't
guess.
do I didn't write a single function that
And the
tells
types
me
are
Wait,
what is
crazy.
going
You
to
can
return.
do like the limit, like the size of something. Like
Man, I guess you saw some examples a few times, Lemos. Like,
Of a
for
function that tells
example,
me what I'm going to return, I have no memory of
no,
that.
about the idea of the Lisp with the type system and stuff. For example, the typed racket that Maget showed the other day, dude.
No, but
no, but
I
that's
saw
bracket,
all
right?
of those
Like
after we
yeah,
made it. So,
yeah,
but
okay.
There.
so if the commander is saying that Lisp has the capability of you can put the types in the code like that, that I need to research because I'm completely not aware of that.
On the thing I was doing with Commander, there is an example. You were there, man. I
I
remember you
have
were there.
I have no memory, like I said.
Yes.
Anyway, so but even though I'm completely fine with the syntax, I actually like the syntax, but I typed so many times, so maybe I'm biased. I don't know.
By the way, I
If you're
think
gonna
the audio
have,
got duplicated.
I well, I don't know then.
On the second part, but anyway, that's fine.
Okay, so I think we are done then. You can finish the recording.